All right. 1, 3. Big idea 1. What was our theorem that went with the 3 angles in any triangle? Everybody better remember this one. Lexi? They add up to 180. The measure of angle 1 plus the measure of angle 2 plus the measure of angle 3. Always, no matter what kind of triangle you have, will add up to 180. Second big idea. Which angles in this picture are the vertical angles? And then what was true about vertical angles? Jimmer.
2 and 4 are the vertical angles.
And?
They're congruent.
They're congruent. How about 1 and 3?
They should be congruent too, right?
Are they vertical?
No.
Yes.
Or, yes.
Yes, they are. Any ones across from each other are the vertical, and they are congruent. If you had me, I always called it VAC, vertical angles congruent. You had our VAC theorem. I think Mr. Drew made you guys write it out, vertical angles congruent. That's all okay though. So, angle 1 would be congruent to 3 because they are vertical, and angle 2 congruent to 4 because they are vertical. Onward. Parallel lines. Do you remember our marking to show that lines are parallel? Adam? No, it's for congruent. No.
It's the arrow.
It's a little arrow. I feel a little filled-in triangle. Arrow. And then we had transversal. 8 angles are created here. We had special angle pairs where one angle came from the top and one angle came from the bottom set. Do you remember any of those special angle pairs? Adam?
I just remember, like, wouldn't it be like if you used the 6 and the 1, they would be like supplementary?
You're close. Not 6 and 1 though. Anybody remember any of those? Yes. 6 and 3 are supplementary. Do you remember what they were called? You are correct. Same side interior angles. I called it SSIAS. They're supplementary. So that means the measure of angle 3 plus the measure of angle 6 would add up to 180. Where is the other set of same side interior angles at? 4 and 5. Remember, the interior is between the lines. So all 4 of these, I'm going to say interior. Maybe that'll help. This is your interior where 3, 4, 5, and 6 are at. 1 and 2 are in the exterior. 8 and 7 are in the exterior. So, our other set of same side interiors are 4 and 5. Okay, that was one special pair. Jimmer?
I don't remember what it's called.
Okay.
1 and 5 are congruent.
1 and 5 are congruent. 1 and 5. Remember I said you could slide them up if they're in the same position. Those were corresponding angles. They correspond to the same position. congruent. I called it CAC. Corresponding angles congruent. So our corresponding would be angle 1 being congruent to 5, because they're both in the upper left, upper left. So again, just think about the 4 angle slid. What overlaps are considered corresponding. So what's corresponding to angle 2? 6. Angle 4 would correspond to angle 8, and then that leaves 3 and 7 corresponding were congruent. 2 more special pair. Alternate, exterior. What was true about them? What was alternate exteriors are? It's either supplementary or congruent. Do you remember? Do you remember? Congruent. There was only one supplementary one. It was the same side interiors were supplementary. So alternate exterior angles were congruent. So they're in the exterior, and they're on alternate sides of that transversal. So what is angle 1 an alternate exterior with? 7. Alternate side of the transversal still in the exterior. And then 2 would go with 8. And our last set were alternate. Yep.
Is it an alternate interior angle?
It is. Alternate interior angles were also congruent. So now we're in the interior, and we're on alternate sides of the transversal, and 1 from each set. So that's 3 is alternate interior with 5. So angle 3 would be congruent to 5, and 4 congruent to 6. AIAC for me. Oh, I got AEAC, alternate exterior angles congruent. And here, alternate interior angles. If you want to write it all out, go ahead. Letters or abbreviations are good for me. Everybody's got that? Which ones did you need to see? Is that good? Okay. So again, we spent a lot of time on those. And I just spent about 2 minutes on it, and you're expected to remember all that stuff. Hopefully. Are we good? Good? Okay. 4. Do you remember how to classify triangles by their angle measure? So if you look at the angle measures in a triangle, do you remember how we classify them? Adam, do you remember one of them?
Actually, aren't there like acute triangles?
Are there acute triangles and obtuse triangles? What other kind of triangles we got? Right triangles. That's not angle measures. Okay, we'll start. Right triangle. What's a right triangle going to have in it? How many right angles? 1. Could it have 2 right angles? Why not? Because if you added 2 90s, you're already at 180. You have nothing left for the third angle, because remember the 3 angles got to add up to 180, so it's going to turn into a square. So 1 right angle makes it a right triangle. Okay. To be an acute triangle, what do you got to have? Yeah.
3 angles smaller than 90.
3 acute angles, or 3 angles smaller than 90, so 3 acute angles makes it an acute triangle. Oops. Acute. 3 acute angles makes it an acute triangle. And then, what about the obtuse triangle? What's it going to have? Adam? One angle greater than 90. One angle greater than 90. So, one obtuse angle makes this an obtuse triangle. And then we did have a special acute triangle. If all 3 angles were the same measure, what would that measure be if they were all the same? Yes? 60. So 60, 60, 60. Yes, it would be an acute triangle, but we also have a special name for it. Do you remember the special name? Nope, that's side lengths. Said equiangular triangle. So we did have the one special one. If all 3 of those were the same, they were all 60s, and that would be an equiangular triangle. Okay. Now let's classify by side lengths. So you're looking at how long the sides are in reference to each other. So what can happen on the side length? Could all 3 sides be the same length? Okay, so if all 3 sides were the same length, that's tick marks. There's your equilateral. But if all 3 side lengths were the same, what do we find out about the angles? They were all the same. So equilateral and equiangular are the same triangle. Just labeled differently, depends on if you're looking at sides versus angles. Okay? What if no sides were the same? Side length. All 3 are different. Nope. What's isosceles? What does it take to be isosceles? 2 sides the same. Anybody remember that one, Jimmer?
Is it scaling?
It is scaling. See, all that information's there. Good? Okay, I'm at the last idea already. Notice I didn't do any examples because I think you're going to know what to do on the homework, but I do have 2 examples at the end. I think it's probably well, maybe because I teach geometry, I think it's the easiest section we've covered. I got 23 years of teaching geometry in my brain, so I forget you guys only took it 1 year. Maybe it won't be as easy for you. Big idea 6. Similar triangles. What did it take for 2 triangles to be similar? Or what does it mean to be similar? Not what it takes, but what does it mean to be similar? The angle measures are the same, so corresponding angles are congruent. And then what was true about the sides? Remember, similar, you're growing and shrinking. Yes?
The sides are similar, which means like they have the same ratio, like 1/1.
Ratio. We had a P word. Start with a P. Meant ratio, though. P word? Grace? It is proportional. Yep. Corresponding sides are proportional. If you can read that. So what that means, draw my 2 triangles over here. A, B, C, D, E, F. Try to draw them similar. So like Ben said, they have the same, when you set up the sides, they have the same ratio. Ratio, proportion, all words for a fraction. So when you set up the fraction of two corresponding sides, that ratio or proportion is going to reduce down to the exact same thing for all three sets. And then C over F. Oh, do you remember the symbol for similar? Forgot to write it down. Yep.
One line.
Just a squiggle is all it is, just that by itself. Similar. Okay, so this right triangle is going to be similar to this right triangle. So these are the kinds of problems you're going to have in the book where it's referring back to one of these 5 big ideas, and you're going to set up some algebra equation and start solving. So, because they're similar, I know that the sides are in the same proportion to each other. So what you look for is a pair of corresponding sides that both have a value. In other words, the hypotenuse to the hypotenuse. So you can set up 35 over 10 as your proportion. If you want to reduce it down, you can before you start, but you don't have to. I'm just going to leave it. That proportion is going to be true. So if I involve the A, and you want to stay big triangle over small triangle, because that's the way I set this one up. I'm going to set it up as A over 6. And then its cross products are equal. Cross product there is 10A. Help me out on 35 times 6. Waiting for somebody to tell me what that is. What? 210. Divide by 10. So we found that side length to be 21. Go back with my same 35 over 10. And then set up a proportion involving the B. So that'll be B over 8. Corresponding sides. Cross products are equal. And then 35 times 8, 280. Divide by 10. Okay, and then the last one I want to do is solving a system of equations, just because it's going to come up when you set up an equation. Do you remember how to solve a system of equations? Say you had 2x plus y equals 15. So if you have two unknowns, I have an x that I don't know and I have a y that I don't know, you have to have two equations. It's impossible to solve and figure out what x equals or y equals by itself. So you've got to have a second equation. I'm going to say x plus 3y equals 10. So you got to take yourself back to, you must have solved systems last year in advanced algebra. You could do it with substitution, where you get like this to be x equals, plug it in here, do all kinds of algebra. Or you could do it with linear combination, where you add the two equations together and you get one of the letters to drop out. That's the way I like to do that. So if we pick linear combination, say I want x's to drop out when I add. Well, right now when I add, I'm just going to get 3x. Adam, remember this?
Yeah, you're going to multiply the whole thing by -2.
Yeah, because what's going to cancel out a positive 2 is a negative 2. So if we take this second equation and multiply it by -2, So, I'm going to keep the first equation as it is. Not going to change a thing there. The second equation, I'm going to distribute in that negative 2. Minus 6y minus 20. Now I'm ready to add these two equations together. So when I add my x's to my x's, they cancel out. 1y minus 6y is a negative 5y. We got negative 5 here. Divide by a negative 5. Y equals positive 1. And now to figure out your x, you can go back to either of these two original equations and substitute in for the y. And just work with the one equation, because then you'll only have one unknown. I'm going to go right here, because it's easy to draw my arrow there. So I'll have x plus 3 times 1, just so you know where it's coming from. That's going to be 3. If I subtract 3 from both sides, x equals 7. So as you're going through the homework, you're going to be setting up a couple of equations that are two equations with two unknowns, and that's just nobody seems to remember how to do that. So, okay. So enjoy your geometry day. Multiples of 3 for homework. Gotta love it when the homework assignment's a problem in itself. Love those. What are multiples of 3? 3, 6, 9. Don't screw it up.
You could do them all.
You could do them all because you have yourself covered.